In this video, we will begin our investigation into power series. A power series is a series of the form given here, where the x's represent a variable and the c sub n's are called coefficients. The observation to make is that what we are seeing in terms of this power series is quite different from the series we've previously encountered because it is a function. That is, based upon an input x, if the series converges, we would then have an associated output. So this very directly leads us into two important questions. Given a power series, can we determine for what x values the series will converge? Stated differently, what is a domain of the given function? The second question that we are going to encounter in future sections is going to be, to what function does the power series converge? That is, it's a function which we'll call s of x for the sum of the series, but for a given series, what is the representation of that function s? Let's look at a motivating example. So below here is probably the simplest power series we can encounter, where we have let each of the coefficients, C0, C1, C2, all become a 1. And the observation to make here is that this is a very familiar type of series. It is a geometric series where A is the first term, 1, and the common ratio R is x. The reason that common ratio is x is if you're at any term, you multiply by x to get to the next. So what we know is that as long as the absolute value of x is less than 1, this power series will converge. So this answers question number 1. What are the x values for which the power series converge? The second question, we know because it is a geometric series, it converges to A over 1 minus r. So we are very efficiently able to answer both of these questions. What we are going to do now is explore our first example specifically focused in on the first question, determining the convergent set of a given power series. So let's find the values of x for which the given power series converges. And the observation to make here is you see powers and factorials. So we're going to go back to our ratio test, and in fact this is going to be a common approach to finding the convergent set of a given power series. So in this case, our a sub n is equal to x to the n over n factorial, and what we need to calculate is the limit as n approaches infinity of an plus 1 over a sub n in absolute value. So this becomes the limit as n approaches infinity. For a sub n plus 1, we go up to a sub n, and each spot we see an x, we replace it with an n plus 1. So that would be x to the n plus 1 over n plus 1 factorial. And once again, instead of dividing by a sub n, we are going to multiply by its reciprocal. So that would be n factorial over x to the n. And immediately we see some cancellations. So observe that n is a positive quantity. So the only portion here that actually needs the absolute values would be the x's. So we have x to the n on the bottom, which cancels off n of those x's in the top. So we would be left with an absolute value of x. N factorial over n plus 1 factorial, we've seen several times previously, is 1 over n plus 1. At this point, we can note we're taking a limit as n approaches infinity. So absolute value of x is a constant with respect to n, and we can pull it in front of the limit. And the limit that remains, 1 over n plus 1 as n approaches infinity, is equal to 0. So in this case, what we can observe is we've applied the ratio test, and what we've seen is the resulting limit is 0. And as long as that limit is less than 1, which it always is, we will be guaranteed absolute convergence. So in this case, the convergence set would be all possible values of x. So the convergent set is minus infinity to infinity. And just a quick recap, if we're asked to find the convergent set of a given power series, as we are here, our approach is typically going to be to apply the ratio test, and whatever we get back, we sit at less than 1 and we solve for x, and that will help us determine the convergent set of the power series. In the next video, we will involve a few more involved examples.